reason why math has an order of operations, or is it just because we decided on that? Okay, so let me start off by explaining what order of operations is about. If you write something like 2 plus 3 times 4, what does it mean? You write 2, a plus sign, 3, a times sign, 4. What does that mean? Well, it could mean add 2 and 3 together, then multiply the result by 4, or it could mean work out 3 times 4 first, and then do 2 plus that at the beginning. What does it mean? Well, if you look at, for example, Wolfram language, our computational language, what does 2 plus 3 times 4 turn into? It turns into the 3 times 4 turns into the function times with 2 arguments, 3 and 4, and then the 2 plus turns into plus of 2 comma times 3 plus 3 comma 4. So that is this thing that is a collection of the function. It defines that there are a sequence of functions that are being used to do those computations. And at that point, it is a feature of the underlying computational language that the arguments of a function are evaluated before the function itself is evaluated. So in that setup, if we got that thing that says plus of 2 comma times of 3, 4, we've defined what order we should do these operations in. But when we just write down 2 plus 3 times 4, there's this question of how do we parse that? How do we decide what that means? Let me give an analogy, actually, that occurs to me in natural language. In natural language, we have to decide, is the times a higher precedence operator? Is it something that's going to grab its arguments first with higher precedence than the plus that is going to sort of come in later? Or how is it going to work? Well, we have the same kinds of issues in English. So we might say, let's see if I can make up a sentence that will have this issue. Let's think. We need to figure out a sentence where there will be a word that can go with 2 different possible things depending on how things are grouped. Well, I mean, there's a sort of a famous one that is a little bit about grouping. You know, I think it was the title of a book about punctuation. A panda comes into some place and eats, shoots, and leaves, which if you punctuate it in one way, it says a panda eats shoots like bamboo shoots and leaves. It could also mean the panda is in the Wild West or something and goes into a saloon and eats, and then comma shoots and leaves. So that's an example in English where it matters kind of how the grouping works, and you can indicate that grouping by a comma, perhaps in that case, but there are other cases where the way the grouping works depends on sort of the conventions about what things mean. So in the case of math, this question of grouping, the person who asked the question here asked sort of, is it arbitrary what the order of operations is? The answer is yes, it's arbitrary. When those notations were made up in the 1400s or so, they just sort of evolved as being, that was how that the times would be done before the plus was done and so on. Actually, when you get into other kinds of operations, when you do things like, actually, it's not so obvious. In some parts of math, it's not so obvious how the grouping works. So for example, if I say 1 minus 2 minus 3, what does that mean? It could mean 1 minus 2 minus 3, where the 2 minus 3 is in parentheses, or it could mean 1 minus 2 minus 3. So that's what's called associativity, which way round things group when you just have a single operator. Just to explain a little bit about sort of the background to this. When what you are basically trying to do is to turn a sequence of characters into something that can be interpreted as this kind of set of functions to apply. in a sense, you've got to turn that sequence of characters into this kind of tree that says, do this, then this, then this. It's kind of like when people learn to do sentence diagramming in English, and you say, this is the sentence. Now let's identify the noun phrase, the verb phrase, the noun phrase that correspond to subject, verb, object, let's say. That kind of diagramming, that sort of hierarchical diagramming, you do exactly the same thing in computer languages, and they tend to operate in a way where they're so-called context-free languages, where basically the structure of that tree that you produce has the property that anytime you have a sort of piece of the linguistics that looks like this, it will be able to have the same subpieces wherever it occurs. In other words, the question of whether that noun could really be broken into an adjective and a noun or something like that, that is allowed to happen. Whenever you have a noun phrase, the noun phrase could be a single noun, or it could be an adjective followed by a noun. Both are allowed, and it's context free. It doesn't matter where that noun phrase occurs, that kind of breaking into the adjective and the noun can occur, that happens wherever the noun phrase occurs. And it's the same thing in computer languages, that they tend to be defined by this kind of sort of thing that says, and now you have this intermediate object that's a little bit like a noun phrase, and it can be decomposed into this, and that decomposition works wherever you put it. So the problem of parsing is the problem of how do you turn a string of characters like 2 + 3 × 4 into this hierarchical thing that will eventually be plus of 2, times of 3, 4. How do you arrange that that transformation to happen? Okay, so the thing you have to decide in 2 + 3 × 4 is which operator binds more tightly, which operator has higher precedence, which operator should be used first. And the convention is that times is used before plus. Now, if you have a single operator, like something like 1 - 2 - 3, then you have the question of what's called associativity. How should the pieces of that minus sign being used, how should they associate? Should it be 1 - 2 - 3, or should it be 1 - 2 - 3? Okay, so in the case of subtraction, it's usually taken to be 1 it's usually taken to be 1 - 2 - 3. Let's do division. Let's say you've got 2/3/4. What does that mean? Does that left associate in the sense that it's, what did I say, 2/3, and then that whole thing /4, or is it 2/3/4? And the results are different. They're mathematically different things. So it matters whether it's left associative or right associative. In the case of division, it's usually assumed to be left associative. Okay, let's do one more example. Let's do power. Let's say you say 2 to the power 3 to the power 4. Let's say you write that as 2 wedge 3 wedge 4. What does that mean? That's actually not very well defined in standard math. Nobody really usually talks about what that means in standard math. So if you make a computer language, you have to make the decision, what are you going to have that mean? If it was 2 to the power 3 all to the power 4, left associative, like slash and minus, that wouldn't be so useful, because 2 to the power 3 all to the power 4 is the same as 2 to the power 3 times 4, just as a mathematical fact about powers. So it's more useful to say that power right associates, so that 2 wedge 3 wedge 4 is actually the equivalent of 2 wedge parenthesis 3 wedge 4. And I should explain, perhaps it's obvious, that parentheses are the way you sort of specify how things are going to be grouped. You often write things without parentheses, but if you want to say, instead of the 2 + 3 × 4, if you wanted to say, I want the 2 + 3 done first, you put 2 + 3 in parentheses and then say times 4. So that was anyway, the concept here is this. There's this notion of precedence, of operators, like plus is below times in precedence and power is above times. So that means that that a power gets done first, binds more tightly, and so on. So you might ask, how are the precedences of all these different operators that you see in math books, how are they determined? it's actually a very strange thing. I looked at this in the 1990s because we were introducing all kinds of exotic operators into Wolfram language. And I wanted to know, were people even consistent in the way that, a circle plus, what the precedence of that was relative to a co-product symbol, relative to all kinds of different things. Were they consistent? The answer is there is a surprising degree of consistency in the mathematical literature. There's actually a correlation with something else, which is when people typeset operators, they usually use just a little bit more space if the things have lower precedence, if they bind less tightly. It's a sort of more airy presentation, as if to say, oh, this thing isn't going to be as grabby with its arguments. It's a looser kind of thing. So in the end, this question of what is the precedence of operators, which is the fancy version of what people learn as order of operations in elementary math, that's something that was determined historically. And some things are more useful than others. Like the example I gave you of power, it's more useful to say it's right associative than that it's left associative. In the case of subtraction, it's more useful to say it's left associative because it's super confusing if it's right associative, and 1 minus 2 minus 3 computes the 2 minus 3 first and then says 1 minus the minus 1, and then that's actually 1 plus 1, and it's very confusing, and it's not what you typically want. So one tries to pick precedences and associativities to be kind of what people expect, and people have been surprisingly consistent in what they want in those regards. Now, the question of which mathematical operations get actual symbols, individual symbols, for example, that's another interesting question. And in the history of mathematics, for a long time, there wasn't mathematical notation. People would just describe things using words. Mathematical notation was invented 1400s to 1600s mostly. And it was very important for the communication of mathematics. People, before that time, people had a hard time really discussing algebra and quadratic equations and solving them and all those kinds of things. Quadratic equations had been studied in antiquity, but the sort of streamlined treatment of them using algebra really had to wait for people to invent these notations like plus signs and equal signs and things like that. It's worth realizing that that invention of that notation was in some ways quite arbitrary. I mean, for example, the equal sign, this is equal to that. Great, it's a nice sign, we all know it now. There's also the greater than sign, which means, A is greater than B. There's a sort of a, it's kind of a V turned on its side with the big end towards the A and the little end towards the B. That means A is bigger than B. So that people had various notations for equality that were sort of the notion of equality now is kind of like, instead of having a greater than sign with a big end and a small end, the equal sign is like equal kind of size on both sides. It's like there's an equal separation between the lines on both sides, and that's kind of how it's indicating that this is equal to that. And the thing that people had different notations, like there's a chap called Gottfried Leibniz, who's the guy who invented the integral sign, for example. He had a notation for equality and inequality that was based on having a scale, a scale for measuring weight, where the scale will be down on one side and up on the other. So it would be like, this is bigger than that. So the scale is lower on that side than on the other side. And if it's equal, the scales are sort of level. So he had notations where he had things going down on one side, up on the other, rather than at the notation that kind of survived, which was the bigger on one side, smaller on the other. And it's worth realizing there's a lot of tricky stuff with notation. Like if I write A equals B equals C, you might think, what does that mean? Does that mean that A, B, and C are all equal to each other? Or does that mean A is equal to B and B is equal to C? Well, okay, because of the properties of equality, that means all three of those things are equal. But when it gets a little bit more elaborate in what we mean by equality, it's not so obvious that all three things should be the same. And it could be the case that they were just the same in pairs and so on. And again, those are a bunch of conventions that one has to pick explicitly when one's making a computational language. When one writes math, one usually just sort of hopes for the best and assumes that if there is some ambiguity, people will understand it from the words around it. But there are different notations that were invented. Like I mentioned, Gottfried Leibniz invented the integral sign. He also invented the the d by dx kind of notation for derivatives. And it's pretty famous thing, you know, when people learn calculus and they learn dy divided by dx, then the immediate thing that people say is, well, I know standard algebra, why can't I just cancel the d's? Well, you can't, because they represent infinitesimals, and there's a whole story about how calculus works. But Leibniz, when he invented that notation, was very concerned that people would just cancel the d's, which has been a long-term problem in learning calculus ever since. Leibniz was also very down on the chap called William Oughtred, who invented the times sign, because he said, people, it's going to look like an X to people. How are people going to distinguish it from an X? And he had a good point there. But in fact, the times sign has survived even despite that ambiguity. So the history of mathematical notation and these conventions about mathematics is a story very similar to the history of natural language, where it was things were introduced, things took on, became popular, and so on. There was some amount of design done. I think we know a lot more now about how to design computational language. I like to think we do. And so many of the things, many of the mistakes that could have been made in the past, we wouldn't make today. An example where was something of a mistake, where you're defining, there was a language called APL, developed by a person called Ken Iverson in the 1960s and a little bit beyond, which was an attempt to kind of provide a notation for algorithmic kinds of operations. And he invented a very large number of new sort of symbols like plus signs and times signs, except he'd have, you know, a triangle up with a line through it. And he'd have some kind of different kinds of Greek-like letters, slightly modified and so on. And the problem was that there were a lot of good and interesting ideas, but there were just too many that came too quickly, and people just didn't learn them and couldn't understand them. And when you first see it for the first time, it looks like some weird hieroglyphic script, so to speak, that you couldn't possibly imagine decoding. But okay, that's a little bit comments on why math has an order of operations. There's some, let's see, yeah, that's probably the, okay, so one of the other issues actually, which I'm slightly sliding over, is that when you say something like 1/2/3, one feature of that is that the slash operation always has two arguments. You're always dividing this by that. For plus, it can actually be an n-ary operator where you have any number of things all being added together, sort of together. You can decompose it as you're adding the first two things together, then you're adding one more onto that thing that you've already made, then you're adding one more to that. So it can be decomposed into a series of binary operations. Plus has the property that it is associative, so it doesn't matter whether it's been decomposed into those binary operations or not. It doesn't matter in which order you decompose it. You could arrange the parentheses in different ways, and you'll still get the same answer for plus, because plus has this property of associativity. It is not the case that these different operations have the feature that it matters to the answer, whether you do, in the example with plus and times, whether you do the times before the plus or the other way around. That matters to the answer. You can invent kind of operations in mathematics where it doesn't matter what the order is. Just like the example of plus that I just gave, it doesn't matter. The answer that you'll get by doing this addition is the same regardless of how you collect the numbers together. And so you can set up mathematical operations which have this feature that it doesn't matter what order you do the kind of collecting together in, but the ones that are typically useful in mathematics, only some of them have that feature, and they don't have that feature relative to each other, so to speak. And by the way, when you do have that feature, it has a lot of very cool consequences. When you do have this feature, you can sort of do it in any, you can sort of collect the things together in any order. It has a big consequence in the amount of, in how you actually do computations, because it allows you to kind of clump pieces of computations together. And often something where it would take you, for example, let's say you have n things that you have to do something with, it might take you n squared operations to do it if you had to do sort of each piece separately. Because you can clump in different ways, you can reduce that to n log n, to much faster computation. So that kind of ability to associate and clump things in different ways is pretty important in practical computation. But in general, you could imagine a mathematics where the order of operations never matters, because all the operators that you deal with sort of have this property that they sort of associate to distribute over each other and so on. But that's not the mathematics that we actually have. And you can ask the question, well, why isn't it? And that's something that once you have things like integers, whole numbers, and you're doing, so the operations that you do on integers, you might say plus, times, power, where do these come from? Why are they the natural operations to do? There's actually a very good reason for that, which is if you say 2 plus 2 plus 2, you do it 3 times. Well, iterated addition, 2 plus 2 plus 2, 3 times, is 3 times 2. So in other words, multiplication is iterated addition. What's iterated multiplication? 2 times 2 times 2. That's a power. That's 2 to the power 3. So it's a very natural sequence. The beginning of the sequence is the pure successor operation. Just add 1 to an integer, a very basic operation on integers. And so repeated successoring is addition. So you're saying plus 1 plus 1 plus 1 plus 1 a bunch of times. And that's so you're let's see, how does this work? When you do but basically you're successoring multiple times. That makes an integer. You keep successoring. That adds another integer to it. So in a sense, addition is repeated successoring, and multiplication is repeated addition. Powers are repeated multiplication. You can ask, what are repeated powers? That would be like saying 2 to the 2 to the 2 to the 2 some number of times. That operation is sometimes called power towers, sometimes called tetration, and things get very big very quickly. Like 2 to the 2 is 4, 2 to the 2 to the 2, remember that we're grouping them as 2 to the 2 to the 2. So 2 to the 4, which is 16, and then the next thing up would be 2 to the 2 to the 16, which is 2 to the power 2 to the power 64,000 roughly. That's a pretty big number. And the 2 to the 2 to the 2 to the 2 to the 2 thing grows very, very quickly. So you might ask, can you make a function which just says, like you go from plus to times to power to tetration? What's next? Well, you can do iterated tetration as well. You can actually make a function that where one of the parameters in the function is how deeply to nest this process. Actually, the most common version of this is the thing called the Ackermann function, which was invented around 1920. And it's a function where one argument is basically says how many times to nest, and the other is what to put in it. So it will give you things like 2 to the 2 to the 2 to the 2, or it'll give you 2 plus 2 plus 2 plus 2 plus 2, depending on whether its first argument is saying just do the one level pluses, or the next level timeses, or the next level powers, or the tetration, or whatever else. And that function is sort of an important counterexample to various things, because it's a very rapidly growing function, as you can guess from the way I've defined it. But it's sort of inevitable by the time you have integers that you will have to have orders of operations that differ between these different layers in this kind of hierarchy of iterated kinds of operations. Okay. Well, let's see. There was a question here from Ardol. What does a day in the life of a scientist look like? Depends a little bit what kind of scientist. Let's break it down between experimental scientists and theoretical scientists. So experimental scientists, the big point is do an experiment and make it work. So you might be building apparatus, you might be doing electronics, you might be putting together some complicated piece of glassware, you might be doing those kinds of things to try to set up your apparatus. Then what tends to be more and more the story of doing science is you get data, it arrives in your computer, and you have to analyze it. And so you're doing lots of kind of data analysis. And one of the things that to realize about doing, well, many kinds of science, but particularly experimental science, is, you know, any serious experiment is going to take quite a while. So on any given day, it's very unlikely that you're going to be saying, aha, I made a great discovery today. You'll be building up some whole activity that you'll be setting up this experiment and so on and so on and so on. It might take you weeks, months. If it's a big experiment in some big area of physics or something, it might take 5 years to set up the experiment, and it might involve 100 people setting up the experiment. And it might be some giant thing that costs hundreds of millions of dollars, or it might be a tabletop kind of experiment, but where, again, you have to sort of gradually build up the experiment and so on. And then you start taking data and you realize, oh, there was this thing wrong and the thing doesn't work quite right, and I have to change it. I analyze the data, I see it isn't quite right, I change it, et cetera, et cetera, et cetera. Eventually, you may get results. And then there's the question of, making sure the results are correct. Not, one of the traps is always, you think you're going to get such and such a result. You keep tweaking your experiment. Eventually, you get that result. You say, I'm done. Well, maybe you're not, because actually maybe that was wrong and you've just been tweaking lots of tweaks. You got it to the point where you got what you expect, but you should keep checking it to make sure it really was right. But I think a decent fraction, I don't know what fraction, I would guess it's probably, average of experimental scientists, probably 2/3 of the time is spent doing data analysis of one kind or another, which means, how do you get the signal out of the data? How do you find that signal from all of this kind of randomness in the data, things like that? That's typical experimental science kind of thing. Theoretical science is, well, again, some people do it in a very kind of pencil and paper type way of, I'm just going to think about this, I'm going to write notes and, sort of do it by hand and so on. I think very much increasingly, and this has been a thing that kind of I've provided the tools for in my life, I suppose, is doing these things by computer and being able to do experiments on a computer where you're setting up some program and you're saying, this program represents the thing I'm trying to figure out. This program represents my model for how this particular system in nature might work or something. Now let me run this program and see what happens. And so a largish fraction of the time is spent making programs, running the programs, trying to understand the results of those programs and so on. And some part of the time is spent, just like in experimental science, it's kind of like designing what you're going to do, understanding the results you get, making conclusions from that. It's pretty rare. I mean, when I do science, for example, I managed to spend quite a lot of my time doing essentially conceptual thinking, and sort of figuring things out at a level. I mean, for me, I find it really useful to do actual examples, and the fact that I'm very fluent in actually doing computer experiments is super useful and much to be recommended for people interested in theoretical science, because that's what you need. And similarly with experimental science, being really fluent in computational language to do data analysis and so on, that's really an important thing, because the question is, well, you've got this data and you're like, well, I just wonder whether if I studied this correlation of that, whether I would see something. Well, if it's going to take you a week to study this correlation with that, you're like, oh, I can't be bothered, I probably don't know what I'm talking about. But if you're fluent enough that it's going to take you 15 minutes, you try it, and by golly, that might be the great discovery, so to speak. So it's really important to be fluent in these tools. And I think people, that seems to be an increasing dividing line in terms of effectiveness in science these days. But then, if you're an actual scientist, you eventually have to explain what you're doing to other people. That means you're writing papers and things like that. I have to say that in my experience, it's worthwhile starting to write the description of what you're doing pretty early, because it helps you to understand it yourself. You have to know sort of the main results you're getting, but then you start trying to write about it. And usually in the process of writing about it, you'll understand it more clearly and you'll get more results. And then in terms of, and now it breaks down in terms of what kind of science you do. If you're an academic doing science, typically your average academic scientist is a professor who makes a living by teaching students. And so that's a part of people's lives. There's also kind of the whole dynamic of going to scientific conferences and interacting with other scientists and so on, and presenting your work. And that's sort of another piece of the process of being a scientist. And so sometimes there's kind of a perk for scientists, like there are often, in the days when there are in-person conferences, there are conferences, scattered all over the world, and there are people who will spend their time, particularly during the summer, hopping from one exotic location to another, going to scientific conferences. I think people find that quite a lot of fun, and there's sort of groups of people in different fields who will frequent the different conferences and so on. It's quite a sort of social scene. I mean, there's much more to say about kind of what it feels like to do science, but I would say that the thing to realize is doing science from a research point of view is a little bit similar, but not that similar to doing science in an educational kind of, I'm going to do the exercises in the textbook kind of way. Because one feature of exercises in textbooks is, they've got answers. It isn't the case that you might get in some direction where you're going and it's like, oh my gosh, there may just not be any way to answer this question because nobody's ever done it before. And when you do research, you're constantly in this, well, maybe nobody actually answered this, and maybe there just isn't an answer. Maybe in the current state of whatever it is, mathematics, physics, science, whatever, maybe we just can't answer this question. Maybe we have to come back in 50 years and then we might be able to answer it. You never know. And so it's something where it takes a big part of the skill of doing research well is to have some idea what's going to be answerable, what's not, what are the right kinds of things to study, what are the questions which are going to potentially have interesting answers, rather than having answers where the answer is, oh, well, it depends, there isn't a definite answer type thing. And then once you have some idea of what the answer, what might be worth answering, the question is, what kind of rough methods might you use? Are they methods you already know? Are there methods you have to go and learn? Is it going to be something where this is going to be a huge project and you're making a huge commitment to try and study this? Or is it going to be something where you're just going to do it as a little bit of fun that's going to take you a couple of weeks and maybe you'll get a good result or not? So those are some of the kinds of things. I would say that for me personally, insofar as I do science, my day in the life as a scientist is probably very untypical because I'm not, for example, I'm not a professor type. Instead, I'm a tech company CEO. So the part of my time that isn't doing basic science is doing designing products and languages and running companies and things like this. But for me, I can usually, like this morning actually, I had I started my day a little bit earlier than usual, so I didn't have an initial meeting. So I spent an hour doing science. What did that actually mean? Well, I was writing a piece of code to try and figure out something that I had sort of a partial answer to, and I didn't quite finish during the hour that I had available. And I wrote this Wolfram language notebook that kind of explains what I was doing so that I can remember what I did. And I have sort of a partially finished result that was looking like it was going in a really interesting direction. And it looks, I'm very enthusiastic about it, but I didn't have a chance to work on it yet. I'll probably have a chance later today or tomorrow to work on it. And I think that's, but one of the things to realize about doing science, I've been lucky enough to be able to do science with good tools and sometimes with good strategy about what to study. And that means the rate of discovering things can be quite high. But one of the things, it's a funny business because you might think, I suppose that if you kind of, if you watched me doing these things, and in fact, I do a sort of this horribly archival thing of recording a bunch of the video from my computer screen when I'm working on stuff, just because I think it's kind of fun to record what actually was involved in figuring things out. And a lot of what you'll see is kind of writing code, debugging code, writing comments about things, making various kinds of, jotting down various kinds of ideas, things like this. But somehow it's very, there'll be some moment when something gets discovered, but often you don't even know when that moment was because you don't have quite the right context to know that was important, or something happens and it's very surprising. And the question is that a discovery, or did I make a mistake somewhere? Or am I confused about something? And it's not something where you say, look, I discovered something. Wow. That happens occasionally, but more often it's something unexpected happens. Let me try and figure out what's going on. Is it a mistake? Is it a confusion, or is it a discovery? And so that sort of blunts the moment of, aha, I just made a discovery this instant type thing. Although that can happen too, and particularly when it comes to sort of understanding how things fit together, that can be something where, for me at least, there's sort of a moment when that discovery gets made. And usually for me, sometimes I make that discovery as I'm trying to write or describe what's going on. That's, for me, a very useful way to sort of unravel what's happening. There's a question here about what's my opinion about reproducible research? Well, so one of the issues is when you're doing experimental science, for example, it's if you say, if I feed the mouse this kind of chemical, then the mouse will be able to do the maze twice as fast, let's say. And you observe that with one mouse, a mouse named Fred, let's say, that happens. Okay, if you used Fred the next day, would the same thing happen? If you used Jane instead, would the same thing happen? If you used, how reproducible is this experiment? How much is it the case that every time you feed the mouse this particular thing, the mouse gets smarter at doing the maze? Or is that something that just happened once? So it's important in making kind of solid conclusions in science that things be reproducible, not least because there may be circumstances. It may be that why did the mouse do the maze twice as fast? Well, maybe it's because it was, let's say, it did the maze the second time in the evening rather than in the afternoon rather than in the morning. And the second time it did the maze, the sun was shining through the lab window and illuminated this different thing. And so the mouse could see the end of the maze more quickly. I'm making all of this up just as an example. And so something you didn't know, you didn't notice that, oh, you did all those experiments in the afternoon and all those other ones in the morning. But in fact, that feature is what made the experiment come out the way it came out. And it had nothing to do with what the mouse had eaten. And so that's a reason to want to do reproducible experiments, to say, somebody else's lab could do the same experiment and their mouse maze will be placed in a different place and they'll have different sort of other factors contributing, and yet they still get the same answer. We just discovered the make the mouse twice as smart drug or something in this experiment. And it's now a reproducible thing that you can take it anywhere and reproduce it. So it tends to be an important thing. And when there are results which are not reproducible, people sometimes say, not interesting, not reproducible. That's probably a mistake too, because there's some pretty major kinds of things that people have studied where they're really remarkable phenomena, really remarkable and surprising effects, where they only happened a few times and they only happened in some particular person's lab, and everybody else says, oh, nobody can reproduce that, must be nonsense. Probably not always the right conclusion. Sometimes it'll be the right conclusion, but often it's not the right conclusion. Often it's just like you didn't think of the critical thing, which, yes, the person who originally did the experiment didn't list that as one of the things that is a feature of how they did the experiment, but actually it turns out to be the critical thing. That, some particular, I don't know, the fact that the lab was in Denver, not at sea level, was the critical thing, and nobody knew that, and or something, and that was the fact that it only happened in the lab in Denver. Well, you shouldn't just say, oh, the person who did the experiment must have got it wrong. It's like, well, maybe there was something we didn't think of that makes that experiment come out that way and another one not come out that way. So it's a tricky thing. Now, it's also worth saying that when you do computer experiments, most of the time, they're just reproducible because you have a program, you run it, it does the same thing. If you have random numbers, and people sometimes get a bit confused about this, which are chosen by the computer, for example, then yes, you run at different times, the random numbers can be different. Like when you do machine learning, it's pretty common that you're kind of using lots of random numbers to pick things, and so things can come out differently. But you can always, on a computer, you can always seed the random numbers. Say, I'm going to use this procedure for making random numbers, and I'm always going to get the same sequence of random numbers because I seeded the procedure the same way. And so then it becomes reproducible. But so typically with computer experiments, reproducibility is not really a problem. That's something I found it amusing when I published my big book called A New Kind of Science that's full of computer experiments, and people are saying, this experiment must be wrong. And it's like, what do you mean? You just run the thing, here's the code, here's the rule that's being used, just run it, you get the answer. Now, that's all well and good if the program that you're running is one that you as a human can read and it's in some nice computational language and so on. It can also be the case that things can go wrong in computer experiments because you can have this giant program and there's a bug in it and it doesn't do what you expect it to do. So if you're doing sort of pure studies of the computational universe, typically the question is, what does this program do? And the program is the program you have, and there's no notion of a bug in the program because what you're actually studying is the program itself. But like famously, when people were studying supernovas, exploding stars, back in the 1970s and 1980s, there were these giant computer codes that were supposed to represent all the nuclear reactions that were happening in stars. And those computer codes said, oh, whoops, stars will collapse and not explode. They couldn't explain supernovas. And eventually that was traced to a bug, just a typing mistake, basically, in this big program that had been used to study supernovas. And so that was an example of where it was perfectly reproducible. You could run the program as many times as you want, and you would end up with the same wrong answer because of this bug in the program. Now, in terms of reproducibility of lab experiments, one of the things that's happening is the increasing automation of labs. I mean, a lot of times still in biology and chemistry labs, there's been people tend to do things by hand. There'll be a pipette. You pipette some liquid from one thing to another, and you put it in these different 96 well plates or whatever else it is, and you're doing a lot of stuff still by hand. But there also are machines that are doing, I don't know, DNA sequencing or whatever else. And increasingly, there's an increasing level of automation in labs. And the more things are automated, the more they will tend to be quite reproducible. Actually, I should give a shout out to a company that uses our technology a lot called Emerald Cloud Lab, that's basically has the mission of completely automating biology and chemistry labs. And they have a very impressive facility full of robots and things for just going from essentially a software specification in Wolfram language of an experiment that you want to do, and then you press go, and things swing into action, and with the experiment is automatically and reproducibly done. Now, so it's an example. I think one will see that I think that will be a very successful effort, and one will see increasingly in biomedical kinds of papers, there'll just be a Wolfram language script that just says, this is the experiment that was done. And it's not kind of a description in words, it's just a script. And you take that script and you run it on sort of any instance of the Emerald Cloud Lab, and it'll get the same result. And that's sort of, I think, going to be an important thing for reproducibility in biomedical science, because doesn't depend on, oh, how well did you pipette that thing and so on. It's done by a machine, which can have well-defined quality control and all those kinds of things. There's one different issue about reproducibility, which has to do with situations where, for whatever reason, you think there's sort of randomness coming into the system. So a classic example is in fluid flow. Let's say you drop a drop of ink into some water. You make this very elaborate pattern of sort of the ink flowing around and so on. The question is, if you do that ink dropping another time, is it going to be the same pattern? Well, if you do it carefully enough, it will be the same pattern. But some things people believe it's essentially impossible to do it carefully enough to make it be the same pattern. They believe that it matters which position in the fluid, which exact molecule in that little ink drop was involved in making it produce this pattern or that. And there's a whole idea, usually goes under the name of chaos theory, that has to do with sensitive dependence on initial conditions. The possibility that if you just change by this tiny, tiny amount, 1 part in a trillion, exactly where that ink drop falls, that eventually, as the whole pattern develops, that eventually some feature of that pattern will depend on that trillionth part of exactly how the thing was started off. And people have believed that sort of some of the complexity of things you see in nature can be attributed to that dependence on the trillionth part, or whatever it is. I think that's actually not really right. That effect does happen, but it's quite rare. And the effect that's much more common is that systems will produce complicated behavior, but they will do so in a reproducible way. It's like, when you compute the digits of pi, it's 3.1415926, et cetera, et cetera, et cetera. That digit sequence is quite random, but yet every time you compute it, it will be the same. And I think that's more what's going on in a lot of these systems in nature. If you do the experiment carefully enough, it will be reproducible. You don't have to get it reproduced at the kind of molecular or quantum type level to be able to get the same result. I should explain, if I'm really going to be complete in answering this question about reproducibility, I should talk about quantum mechanics, and I should talk about the fact that in quantum mechanics, there's this idea that when you make a measurement, that all that the theory can tell you is what the probability of something happening is going to be. It doesn't tell you what specific thing will happen. And that's sort of a necessary kind of non-reproducibility. But in our theory of physics, that story becomes considerably more complicated in terms of how you interpret it, and in terms of the way that we as observers of the universe are, this is going to get complicated to describe this. But I think it's fair to say that there is a notion of reproducibility of what in our theory would be called the multi-way graph. That's sort of the graph of all possible quantum histories, that can be reproducible, but the particular observation that a particular observer makes, because that observer has certain arbitrariness about sort of how they're observing what's going on, what they see may not be reproducible, even though what's in a sense fundamentally there is reproducible. But that's a significantly more complicated kind of question. Let's see. All right, there's a question here. There's a comment here. Okay, this is a more, actually just put live on the web, I might comment. I did some, as part of our annual summer school, I did some interviews with some scientists and others that were initially just intended for our summer school students, but the interviews were kind of interesting. And so we put them out on the web, and you'll find the first set of maybe 5 or so of them that are out there. And I'm actually planning to do a weekly kind of interview with some interesting scientist. I have to say that I have a very sort of personal objective with these interviews, which is I'm trying to learn stuff from them. And I hope the interviews will be interesting and other people will learn things too. But my number one objective and my number one criterion for picking people to talk to is really things that are sort of in the path of things that I'm trying to research and I'm trying to understand, because that kind of gives me among other things, that's as I say, my personal objective there, and also gives me a particular kind of direction for what if one talks to somebody who's been doing interesting science all their life, so to speak, there's too much to talk about in an hour, and so I will be trying to focus these things based on particular things that I'm interested in. So let's see. There's a question here. Wow. Okay, there's a question from Karup. Will teleportation ever be possible? And even if only, say, for a photon stream, So one could send a probe into a black hole and be able to transmit back images across the event horizon or something. Okay, let's explain what teleportation is. Teleportation is you're here now, instantaneously, you're somewhere else a moment later. So you can clearly go from here to somewhere else by just, walking there or getting in a spacecraft and going there. But that takes a bunch of time. The question is, can you instantaneously show up on the other side of the Earth or show up on the other side of the galaxy or whatever else? Is it possible to do something that's like in, the Star Trek transporter kind of idea, where you're one place and then you're suddenly somewhere else? Now, it's worth commenting that even sort of the junior version of teleportation might be, you're here now, you travel at the speed of light to somewhere else, and then you show up at that other place. Right now, if we take light, photons making up light, they're always traveling at the speed of light. But we, made of ordinary atoms and ordinary matter and so on, we don't go at the speed of light. We are made of particles that have mass. Photons have zero mass. Zero mass things go at the speed of light. Non-zero mass things just kind of sit there unless you push them very hard. Then they'll go. Then you can push them, and it's actually, as you try and make them go faster and faster. One of the consequences of relativity theory is that as you try and make something go closer and closer to the speed of light, the amount of force with which you have to push the thing increases dramatically as you get closer to the speed of light. And in fact, you'll never reach the speed of light with any finite force for any massive object. You'd be pushing harder and harder and harder. The thing is going faster and faster and faster. Like the fastest things we do on Earth with particles are in particle accelerators. And there we take things like protons and we accelerate them to 99.99 whatever % of the speed of light. They are the fastest things on Earth, other than photons, are the particles in a particle accelerator. And and so you might say, well, gee, why don't you just take, you and sort of put you in a particle accelerator and wind you up somewhere else? Well, the problem is the only things we have in particle accelerators are individual protons going around. So unless you want to be disintegrated into individual protons, you're kind of out of luck in a particle accelerator. Now the question is, well, what if you could, let's say that you wanted to teleport a lump of plastic, okay? Well, here's how you could do that. You could have a 3D scanner and it could figure out what the geometry of that plastic is. You could turn that geometry, you could just send the signal that says, here's the geometry. You could send it by, a radio or something at the speed of light. And at the other end, there's a 3D printer and it prints out that same shaped lump of plastic. So in a sense, you've teleported that piece of plastic in the sense that you took a version of that piece of plastic, and maybe for extra teleportation points, you can destroy the original piece of plastic. And then it's as if you started with this one piece of plastic, you did all these things to it. At the speed of light, you moved it somewhere else, it was reconstituted there. That's actually, I think, in the kind of backstory to Star Trek. I think the transporter, the concept there is it's sort of breaking things down into individual atoms, sending the information about those atoms and reconstituting at the other end. That's kind of the science fiction backstory to that. So that's one sort of form of teleportation. We don't know how to do it except for things like lumps of plastic right now. Maybe in the future, when we have molecular scale manufacturing, when we can actually construct an arbitrary collection of atoms arranged in molecules and all those kinds of things, maybe when we can do that, which I think will be possible at some point in the future, to do kind of molecular scale construction, sort of atom by atom, we can do that in very simple cases right now with atomic force microscopes. With an atomic force microscope, you can basically pick up an individual atom of, I don't know, silicon or something and put it down in a different place. It's rather slow to do it because you're doing it atom at a time. That's not the best way to build things, but still we can more or less do that, but it requires being on solid surfaces and all that kind of thing. The idea of just being able to say, here's a design, here's a, I've drawn out my design for the molecule I want, press go, make that molecule. we can't do that for arbitrary molecules. There's another special case where we can do it, which is for DNA. We know how to make small sequences of DNA, reasonably small sequences of DNA with arbitrary sequences of base pairs. And the big thing that sort of life discovered is how to take a DNA sequence and use it to make proteins, sequences of amino acids that then are molecules of different shapes and so on. But we don't know how to do that in more generality than the particular of the thing that's been discovered by the evolution of life on Earth, namely the DNA, RNA, amino acid, protein type sequence. But so maybe one day we will be able to reconstruct things at a molecular scale and kind of scan it, figure out where every atom is, send the information about that, reconstitute at the other end. That's one kind of form of sort of junior teleportation, let's say. The other form of teleportation is something where literally somehow the actual thing winds up in a different place at let's say zero, at infinite speed rather than just at the speed of light. Okay, so one of the places where this gets confusing is in quantum mechanics. There is a notion of teleportation. And here's roughly how that works. The story of classical mechanics is always that definite things happen in the universe. You drop a stone, it falls in a definite trajectory. In quantum mechanics, the story is instead of definite things happening like that, all possible things happen. So you drop a stone, and actually there are all these different possible paths the stone could follow. They're all in some sense followed. And the typical way we observe quantum mechanics is through our particular sampling of that set of possible quantum histories. So the thing that, and what we've understood actually from our physics project is a lot about how that sort of structure of quantum histories works. It's a rather elaborate thing where there's sort of, at any moment you can have one state of the universe, it can branch into two, those can branch again, but then different branches can sometimes merge. Different histories of the universe could end up actually in the same state of the universe. And that branching and merging phenomenon, it's a very important phenomenon that leads to this kind of quantum entanglement phenomenon. But the main thing is there's branching and merging of all these different possible histories for the universe. Very confusingly, when we are observing the universe, our brains are effectively branching and merging in the same kind of way. So the story of quantum mechanics and quantum measurement ends up being a story of how does a branching brain perceive a branching universe? And that's a tricky thing. And you can represent it using some of the mathematics, some fairly advanced mathematics that's kind of been emerging from pure mathematics and from quantum mechanics in recent years, and it's now rather clarified in our project. But okay, what happens is in that kind of multi-way graph of all these possible quantum histories, you can sort of lay out the possible quantum histories at a particular moment in time. When I say lay them out, you're not laying them out in ordinary space, you're laying them out in what we call branchial space, the space of possible quantum branches. And that branchial space has many attributes like physical space, but it isn't physical space. And so one of the attributes that it has is just like in physical space, the fastest you can go is the speed of light. In branchial space, the fastest you can go is a new thing that we've realized, which is this maximum entanglement speed. We don't know how big the maximum entanglement speed is. We think it might be around, it's in weird units, around 100,000 solar masses per second. But that's in weird units because the notion of distance in branchial space is kind of, it's not measured in meters, it's measured in other kinds of units. So in any case, so there's this maximum speed in branchial space. It's some value, but it has nothing directly to do with the speed of light in physical space. So what can happen is in quantum mechanics, you can end up with something where different branches in branchial space have wound up in different places in branchial space corresponding to different places, and those different outcomes have some object to different places in physical space. And so, well, it's kind of a long story, but you can end up with something where with respect to the measurements you do, you will appear to have teleported something from one place to another. When you try and sort of trace back what information had to get exchanged, in order to know what measurements to do, you actually have to have sort of a back channel that exchanges information through physical space at kind of the speed of light. But nevertheless, you can do this teleportation protocol will allow you, if you have that back channel information exchanged, then which can only happen at the speed of light, then other things can happen seemingly instantaneously. Although we think actually it isn't really instantaneous, it's actually something related to this maximum entanglement speed, and it will be interesting to try to measure that, and that's a whole different story. But so that's kind of a notion of teleportation that happens there, and I don't think that is that's more of a kind of a trick of how the measurement process works and how these kind of branching brains in quantum measurement work than it is an actual, I'm going to move this from here to there. Now, there are other effects. One, this is kind of tricky, when in our models, space, so in the usual thinking about space, it's just like space is just a place where you put stuff. You can say, I'm going to put something in this position in space, I'm going to put something in this position in space. There's no question of sort of what space is made of. In our models, space, like a fluid like water, is made of molecules. So space is made of a whole collection of discrete points that we can kind of somewhat whimsically call atoms of space. They're not real atoms. They're something much more conceptual. They're just geometrical points that define the content of space. Okay, so what then can happen is, and this is now going to get a bit tricky, but what then can happen is there's this question of what does it take? Well, I wrote this whole piece actually last year about faster than light travel in our models. And I think this would take me a while to explain how this works, but well, I'll give it a try. So, okay, how is space? What is space made of? Space is all these points, and these points have connectivity information. Each point knows which other points it's, so to speak, friends with. It knows which points are related to which other points. And that's how we define all of space. And the notion that we can kind of think of space as this thing which is laid out and where we go from here to there to the next place, that's all sort of emerging from a large number of different geometrical points with all these different connections. Okay, and the way it works is at every moment, space is being recreated. There are little updates that are happening of those connections are getting changed to other connections. And at every moment, everywhere in space, there are those updates happening. If it wasn't for those updates, space would not be knitted together. We wouldn't be able to have a notion of adjacent pieces of space and things like this. That's a consequence of continuing activity in space. And in a sense, most of the activity of the universe is actually the maintenance of space. All the things that we're familiar with, you know, electrons and quarks and all those kinds of things, those are just some, you know, trillionth piece of everything that's going on in the universe. Most of what's going on in the universe is essentially the maintenance of space. And in a sense, if we had a way to look at it sort of microscopically, what we would see is that it's like kind of molecules in a gas. They're all just bouncing around, but together they have the effect of making this gas, and it has a certain pressure and so on. Similarly, we would see all these atoms of space doing very complicated things, but together they make something which kind of seems like space as we experience it. Okay, so the tricky thing is, let's imagine we're just looking at molecules of gas in a room. And we say, I want to ride a molecule from one side of the room to the other. Okay, so most of the time in air, for example, at standard pressure, the mean free path of an atom or a molecule is very short. So most of the time, most air molecules will go a tiny, tiny distance before they hit another air molecule, and then they'll hit another air molecule and so on. And as each time they hit an air molecule, they'll be sent in a random direction. And so if you're riding an air molecule, it's going to follow this kind of random walk from one side of the room to the other. It's going to kind of just, and that means that it's going to go rather slowly from one side of the room to the other, because sometimes it'll go forwards a step, it'll go take one step forward, one step sideways, one step back, and so on. And the average distance that you go after a time t is about square root of t. It goes slowly. Okay, well, but if you were very clever and you could kind of see all the molecules in the room and you could pick particular molecules, you say, okay, I'm going to go on this molecule for this micron distance, and then I'm going to hop to this other molecule, I'm going to ride it for the next micron, and then this molecule, and then this molecule, and I'm going to predict exactly what sequence of molecules I should follow. Well, then you will not be subject to this kind of random walk. You'll be able to pick a series of molecules. You'll be able to kind of pick these stepping stone molecules, and you'll be able to hop across the room actually at the speed molecules go out, which is basically the speed of sound. So if you were clever enough at the level of molecules, you would be able to hop molecule to molecule and travel through the air at the speed of sound just by riding molecules. Okay, now in practice, we can't do that because it's very hard to foresee what all the molecules are going to do, and we don't have things at the scale of individual molecules, and it's just completely impractical. But it turns out that, well, there is the same kind of possibility in space. There are, just as this kind of all these interactions between atoms of space and so on, if we pick the exact right ones to be associated with, we could go at something which is actually more than the speed of light. The speed of light is more or less the speed that would correspond. It doesn't correspond. It's okay. There's some confusing aspects to this whole thing about the analogy between gas molecules and atoms of space. They're not quite as analogous as I'm making it sound, but roughly there's a speed of light that is the sort of the average speed that the average maximum speed that things go at. But there is the possibility, if you pick the exact right sort of atoms of space to ride, that you could go faster than the speed of light. Yeah, I'm eliding a bunch of things about the way that space is actually made, and you're sort of beating the way that space is knitted. You're finding these kind of tunnels in space that are sort of go outside of the kind of main structure of space. But that allows you to do things where you're going essentially faster than the speed of light. And so if you could make use of those space tunnels, you could teleport. And one of the things people talk about in traditional ideas about the structure of space-time are these things called wormholes. You can't create a wormhole in the standard theory of relativity. You can in our models of physics, because they have more detailed information about the structure of space-time, and so they allow you to understand how you can actually create a thing which has kind of holes in it and so on from a thing that doesn't. You can't understand that in the traditional theory of relativity and the traditional general relativity. But in any case, in traditional general relativity, you can have these wormholes, which are kind of ways in which you can go, like a worm can have a hole from one sort of piece of soil to another. You're going from one piece of space-time to another piece of space-time, sort of in a different path than the traditional one where you're just going through every intermediate step in space-time. One of the downers about wormholes in traditional relativity is that to maintain a wormhole, you need a negative mass thing. You need negative energy. You need something where gravity is not attractive as it usually is with positive mass things. You need something where its mass is negative so that it can have repulsive gravity that is needed to sort of hold the wormhole open. But in traditional models, the only way you get a wormhole is to already have a wormhole. In our models, you can create space tunnels, which are a little bit different from wormholes. They're a little bit of a generalization of wormholes. You can create them without having one to begin with. And in fact, constantly as space evolves, there will be little tiny space tunnels produced all over the place. Whether you can line them all up to make something you can travel through is a different issue. But so that's kind of we're very far away from the technology for being able to do these things. Whether that technology is conceivable to make in our universe, I don't really know, but never say never in terms of what is technologically possible. There are many things, even in my lifetime. I think of gravitational wave detection, for example, where it's like, well, we'll never be able to observe it, but then one can. Actually, another effect that's kind of fun that I was, I talked about the things that go fastest the forms of matter that go fastest on our planet are in particle accelerators. So there are protons whizzing at very close to the speed of light around particle accelerators. Gravitational waves are produced when massive objects kind of accelerate in certain ways. And in fact, there will be gravitational waves produced by particle accelerators. There's a thing called synchrotron radiation, which is usually electromagnetic radiation that comes about when you are making a particle stay in a circular path, because to make it stay in a circular path, it has to be accelerated, because if it wasn't being accelerated, it would just keep going in a straight line. And that process of keeping it, accelerating it, will emit this thing called synchrotron radiation. Usual synchrotron radiation is electromagnetic radiation, it's gamma rays, X-rays, things like that. But there will also be gravitational synchrotron radiation, a tiny amount of gravitational radiation. Actually, I think on the surface of the Earth, the biggest source of gravitational radiation is probably protons in particle accelerators. But that right now looks like a ridiculously, immeasurably small amount of gravitational radiation. I'm sure that in time it will become possible to actually measure that. And that's just an example of sort of the progress of these things that at first seem like they're just sort of too small an effect to ever be important. But then it turns out that eventually one can measure them, and sometimes even make use of them for technology. Well, I think we're getting to the end of our time here today. So many interesting questions. All right. Well, I think we have to leave these for another time. I might say for people who are who find these answers interesting, we have been posting previous iterations of these live streams, and actually through some nice technology that we have, there are word clouds generated from the transcripts, from the automated transcripts of the things I've been talking about. So you can kind of see, if you scan through the episodes, you can kind of see what types of questions were being addressed in them, and actually the sort of shortened versions of the questions themselves we're adding in to those to those website entries, so you can kind of find questions you might be interested in. All right, well, thanks for joining me here, and there are lots of interesting questions saved up for next time, and I look forward to more questions next time. And I find it very interesting to give these answers, and I figure out things as I'm describing them. Maybe I should be telling you when I figured out things I hadn't figured out before. Today there were 4 or 5 of those, but they're kind of not relevant to what's being described. They're just relevant for me internally, because it's like, oh, I hadn't noticed that connection before. Anyway, look forward to seeing you all